This week, our presenter is Tom Morrison. Tom is a senior physics major here. He's been working on computational astrophysics research with Professor Workman. And the title of his talk, give me a minute, it may take a minute to read this, using magnetohydrodynamical computational methods to stimulate the interstellar gas cloud G2 as it encounters a supermassive black hole at the center of the galaxy. So anyway, without further ado, let's welcome our speaker for today, Tom Morrison.
All right, so as Dr. Middleton said, my name's Tom Morrison. I'm a senior physics major here. That being said, this is the end of the semester, so I haven't slept a lot. So if I fall asleep, just throw a book at me or something to wake me up. I've already had 3 cups, so I should be good. So anyways, my senior research, what I wanted to work on this semester was dealing with computational astrophysics. I wanted to work on this project for a couple different reasons. Number one, I'm very interested in the space sciences. And number two, I wanted to gain some computational physics background. So I decided to work with Dr. Workman on a project. And our specific project that I'm going to be talking about today is simulating an interstellar gas cloud G2 as it interacts with the supermassive black hole at the center of our galaxy using magneto-hydrodynamical computational methods, as Dr. Middleton read off. Okay, so this is just an outline of what I'm going to be talking about today. I'll start off with some background information about black holes, some background information about interstellar gas clouds, and then what happens when those two things interact with each other and form something called an accretion disk. Then I'll be giving an MHD overview, or magnetohydrodynamics overview, quick overview of what that is. And then I'll finish the presentation with talking about our research, our simulations, data analysis, and where we're headed next. All right, so first and foremost, what is a black hole? I know a lot of people might be wondering that. The real answer to this is nobody really knows. But if you ask a physicist, we like to sound smart, so we may tell you that a black hole is an object whose radius is smaller than its Schwarzschild radius, where the Schwarzschild radius comes out of Einstein's theory of general relativity and is given by this equation here, 2gm over c squared, where g is the gravitational constant, m is the mass of the object, and c is the speed of light. So what this equation is basically telling us is if you have an object of mass m, and you compress that object into a sphere with radius rs, essentially the escape velocity from the surface of that sphere is going to be equivalent to the speed of light. So what that means is a black hole is basically just a very dense, compact region of space that has such a large gravitational potential that not even light can escape its potential. And to kind of give you an idea of what that means, give you a visualization. If you wanted to turn the Earth into a black hole, you'd have to compress the Earth down into about the size of a marble with the Schwarzschild radius of about 9 millimeters. Okay, so when we're talking about black holes, we usually break them up into 2 types of categories. The first being a stellar mass black hole, which is about roughly the mass of a few times the mass of our sun. And there's estimated to be some 100 million in our galaxy alone. And then on the other opposite end of the spectrum, you have a supermassive black hole, which is what we're going to be interested in our research, which is roughly the mass of a small galaxy. And scientists now believe that there's one of these supermassive black holes at the center of every galaxy. And the supermassive black hole at the center of our galaxy in particular, the Milky Way, is given the name Sagittarius A. It's about 25,000 light years from Earth. It was discovered in 1979. And to give you an idea of how big this thing is, it's about 4.3 million times the mass of our sun, and has a Schwarzschild radius of about 13.3 million kilometers. So if you remember, you compare that to the Schwarzschild radius of the Earth, which is about 9 millimeters, you get an idea of how huge this thing actually is. All right, so next I'm going to kind of talk about the process in which these things gain mass. It's still an ongoing branch of research in astrophysics, but it's pretty well understood that these black holes can gain mass through accretion from nearby objects, such as interstellar gas clouds, like you see here in this picture. So what is an interstellar gas cloud? Really, an interstellar gas cloud, that's just a fancy term for a region of space that's denser than the surrounding regions. When we're talking about interstellar gas clouds, we usually break them up into two different categories, diffuse and dense clouds, where a diffuse cloud is consisting of neutral or ionized atomic hydrogen, which you can just think of as a plasma, or a dense cloud consisting of molecular hydrogen. So the interstellar gas cloud that we're most interested in, and for our specific research project, is a small diffuse ionized hydrogen cloud called G2. It's roughly 3 times the mass of Earth, and the reason why this is such a why we're so interested in it in particular, is there's a pretty awesome thing that's about to happen, or may have already happened, but this gas cloud is essentially on a crash course with the supermassive black hole Sagittarius A. So this will be the first time in 40 years that we're actually going to be able to observe this event happening. So it's a pretty exciting time in astrophysics and astronomy, because we're actually going to get to see the effects of a black hole interacting with an interstellar gas cloud. So now I've given you guys a little bit of background information about black holes and interstellar gas clouds, which are really cool topics in and of themselves and could constitute a talk all by themselves. But what we're more interested in for our research is what happens when these two things interact. So, as you might imagine, the problem here is you have a lot of volume with your interstellar gas cloud and a lot of material trying to go into a very small volume, the black hole. So I like to use the analogy of a toilet, flushing a toilet, to kind of wrap my mind around this. But basically, what's happening is the same thing in your toilet. You have all that water, whatever else may be in that water, that needs to go down into the plumbing, so a very small volume. And when you flush it, you end up with this swirling process, and it eventually makes its way down into your plumbing. So the same sort of thing happens in space when you get this interaction between an interstellar gas cloud and a black hole. You get what we call accretion disks. So an accretion disk is just a structure formed around a central massive body in which dissipative forces within that structure, usually attributed to viscosity or friction, causes the material within that accretion disk to spiral inwards, just like your toilet when you flush it. So, and then during this process, you get gravitational potential energies being converted into thermal energy. So you're getting, the disk is heating up and producing a larger luminosity, which is ultimately what we're going to be looking at. All right, so that's more or less the background information of our research. So from here on out, I'm going to be talking about our research in particular. Threw this in here. The school is gracious enough to provide me with my own office. And they even gave me a portrait of myself drawn by Daniel Cicero. So that's where I've spent the last semester, pretty much. I slept there a couple times. But, all right, so the ultimate goal of our research of this project kind of comes in 2 parts. Number 1, we want to be able to get a reasonable prediction for the energy distribution spectrum of this interstellar gas cloud accreting onto the black hole. And then number 2, we want to find from our predictions, can we even observe this from Earth? And if so, at what wavelengths? And this is a pretty cool project, in my opinion, because we can actually compare our results to observations in the near future. So magnetohydrodynamics, big, ugly word. What is it? Magnetohydrodynamics is basically the study of the dynamics of an electrically ionized fluid. So what that means is you have a magnetic field within your fluid, and that magnetic field is going to ionize particles within there, and it's essentially going to apply forces to your fluid that are going to affect the dynamics, which will affect the dynamics and also affect the magnetic field itself. So what this is saying, it's basically the equations of magnetohydrodynamics are just a combination of Navier-Stokes equations for fluid dynamics and Maxwell's well-known equations of electromagnetism combined into a system of equations. So these are just a few of the magnetic or MHD equations that we're going to be using in our simulation. You may recognize the top one as a continuity equation, basically just conservation of mass. The second one is basically just a conservation of momentum, and this is where your gravitational potential from that supermassive black hole comes in, because you're going to have an increase in momentum, so that's over there on the right side. This third one you may recognize is a variation of Ampere's law of induction. And the last one is important to note that this E here is not electric field, it's actually energy. So it's basically an energy conservation equation. And if you want to see the variables, they're all over here. G is the gravitational potential, B is the magnetic field, B is the bulk velocity, rho is the mass density, E is the energy, like I said, and P is the plasma pressure, T is time.
So you don't have to worry about electric fields at all in that equation?
Well, more or less no. It's you're basically converting from electric fields into magnetic fields. Why MHD? First and foremost, it's a fluid-based code, which is good because ultimately that's what we're dealing with, a fluid in the interstellar gas cloud. Second, MHD allows us to take into consideration the magnetic field strengths that are going to be affecting the dynamics of this fluid. And thirdly, MHD allows for redistribution of angular momentum, which is really important in accretion disks, through a process called magneto-rotational instabilities. What that basically means is you have a turbulence within the fluid that allows for this redistribution of angular momentum, which we observe. So our simulations, we used a fluid-based code called Athena. It's basically a grid-based fluid MHD code solver in either 1, 2, or 3 dimensions. And we ran our simulations on a 24 parallel processor Linux machine. So the first thing we had to do is determine some initial parameters, as you can see up here. We basically initialized the gas cloud as a spherical blob with an initial Gaussian density distribution, radius of 6.1 times 10 to the minus 4 parsecs, which parsecs is just a unit of measurement in astronomy. And we set it at an initial separation distance of 0.0125 parsecs from Sagittarius A. And all of this data is coming from astronomy observations in 2011. And then we initialize its temperature, 550 Kelvin, separation distance, and we initialize its velocity in the x and y direction. And we set it on this grid space. Our grid space is 640 grid spaces in the y direction by 3,104 in the x direction. And it's important to note here the asterisk with not to scale up in the right-hand corner, because if this was actually to scale, the black hole would be in the other room. So then we initialize all our parameters, we hit the start button, and what's actually happening within the code. The code determines an appropriate time step for each iteration. The time step it determines is just takes the grid spacing between 2 grid points, divides that by the maximum velocity or the maximum sound speed or the maximum Alfvén velocity. And at each grid point it solves for these variables, so the velocity in 3 dimensions, the magnetic field in 3 dimensions, density, and pressure. All right, so we let it run, and finally we get our results. This is going to be a video, so I'm just going to set the stage for this video, just to give you an idea of how much computational processing time is going into this code in particular, or this simulation in particular. This simulation took 7 days to run on 16 processors, and essentially it's solving those 9 MHD equations at every single grid point, which there's roughly 2 million grid points, and it's doing that at every time step. In this simulation, there's about 200,000 different time steps. So it's a crazy amount of computational power going into just this one simulation. And this is what we end up with. Oh, and you're looking at the density distribution.
Where's the black hole?
You can't see it, you'll see it in a second. I could kill some time and just keep letting it play. But I'll go ahead and move on. So some of the initial problems that we ran into with our initial simulations where we were having, because of the large separation distance between the black hole and the small size of the cloud, we were having far too much computational time and not enough resolution. So we decided to go back in and add a computational method called static mesh refinement in order so that we could basically zoom in on the area that we're interested in. So what you basically do, in our case, we're interested in the area around the black hole. Put a box around that black hole and double the amount of grid points within that box. So then after doing that, this is the exact same simulation, but now this is using static mesh refinement, so it's zoomed in one level. Same simulation, just zoomed in. And so with this better resolution, you can more effectively see what's happening with the density.
So the colors are what? Yeah.
They're just different levels of density. So
It's most dense at the center, obviously.
right.
So there's not much dissipation here? The gas doesn't seem to be making its way in?
Yeah, that's one of the things this is more of an initial, we're just trying to see if we can get the code working, but yeah. One of the things we need to go back in is add the accretion rate so that material is actually being pulled out of the center. All right, so we can make, from our simulations, we can make really pretty videos. That's awesome. We're pretty stoked about that. But what else can we get out of these simulations? So I'm going to spend a few minutes talking about our data analysis, what we plan to do. We haven't done anything yet. But this is kind of our plans, where we're headed. So first, we want to see if we can create a spectral energy distribution, which a spectral energy distribution is just basically a plot of the energy flux density versus wavelength or frequency. And it's commonly used in astronomy to characterize astronomical objects. And in order to do so, we make the assumption that each ring within the disk, annulus ring, is radiating as a black body at that local temperature. So if the disk extends from an inner radius to an outer radius, the spectrum is just the sum of these black bodies weighted by the area of the disk, which is given by that equation there, where b of lambda is the well-known Planck function from modern physics, and it's given by this equation here, where h is Planck's constant, c is the speed of light, lambda is the wavelength, k is Boltzmann's constant, and t is temperature. And since we haven't produced any of our own spectral energy distributions, I decided just to throw up a slide of what this is going to look like. So here you have the formation of a low mass star, basically going through different processes, and an energy distribution for each of those different processes. So that's where we're headed. And we need to, so in order to create this SED, or spectral energy distribution, we need to determine a temperature. And so in order to do that, we have our accretion disk, which you see in the picture. Again, not to scale, but we want to find the temperature at each of those grid points. And if you remember, MHD, the code's not actually solving for temperature. So in order to get temperature out of our simulations, we assume that the gas is adiabatic. And then from thermodynamics, we know that the sound speed squared is proportional to the pressure over density. And replace pressure with your ideal gas law, and you get this relationship where gamma is the adiabatic index, K is Boltzmann's constant, T is temperature, mu is the mean molecular weight, and MH is the mass of hydrogen. So then you do some algebra, rearrange, end up with an equation for temperature. Now we can solve for temperature at each grid point. So this is just a zoomed in grid space of that previous slide. Now we have the temperature at each of our 4 corners. So then we can find the average temperature for each grid space by simply adding the 4 corners and dividing them by 4. And then you can find the corresponding Planck function for that average temperature for each grid space given by the Planck function. And then simply sum all those up, weight them by the area, and that'll give you your spectral energy distribution.
How close to the black hole are we? Are you taking into account any distortions by general relativity to the area, or it's just Euclidean?
We're just neglecting those.
How do you get back to the previous slide, the temperature? You need the sound speed. Is that you get that out of your? I presume you get that out of your.
Right. So the MHD equations we are solving for density and pressure, which is essentially what sound speed is.
But are you assuming no heat transfer?
Right, we're assuming no heat transfer. All right, so back to this slide. So we have our disk spectrum given by the sum of all those local black bodies at their temperature, weighted by the area. And then we can determine the total luminosity by simply integrating from 0 to infinity over all wavelengths. And this is good because then we can compare this to observations. All right, so that's nice. So we have our expected total luminosity, but that's only for if the disk is at an angle of 90 degrees to our line of sight. But what happens if that disk is not at that angle of 90 degrees? Maybe it's at 45 degrees or 0 degrees. So we have to make basically predictions for if the disk is at 45 degrees or 0 degrees. And to do so, it's not quite as straightforward. We're going to have to use everyone's favorite astrophysical equation. If you're taking astrophysics, you probably love this equation, the radiative transfer equation. And so that's where we're headed in the future, so that we can basically make a range of what that our predicted luminosity would be. All right, so what's next? Obviously, we want to finish our predictions, and then we want to run more simulations, possibly utilizing supercomputers at other schools so that we can increase our computational time and run lots and lots of simulations. And then we can vary the initial parameters. One of the initial parameters that we're especially interested in is magnetic fields. So we want to vary that magnetic field and see what effect that has on the dynamics of the cloud and what effect that will have on the total luminosity. Yeah.
So I was wondering, your grid, does it have a z direction? It's got x and y. Do you have a z direction also? I didn't quite follow all of it.
No, it's just in 2 dimensions, so it's x and y.
You wouldn't be able to model the beaming you sometimes get off the axis of black holes. It's just 2D.
Nope. Yep. And I actually did a little bit of personal research into that, and it's not well understood what that beaming comes from. So, yeah. Yeah, so I'd just like to acknowledge Dr. Workman for his incredible patience and help in this project, as I started with basically no computer experience at all, and I didn't even know how to log on to the computer. And so he's been incredibly patient, incredibly helpful, and I've taken a lot away from that, so thank you, Dr. Workman. And yeah, any other questions?
Should we thank our speakers first? back to those equations, equation slide? They had like 5 of them or so. I think you've already actually answered this, but I just wanted to check. So on the second one, you have G on the right-hand side, which is the gravitational potential. Is that just the 1/r potential of Newtonian gravitation, or is there the correction terms from GR included? I think you already nailed that down with saying that it was.
The grid spacing is so much larger than, like the actual black hole, because compared to the grid spacing, you don't get down to resolving
You're far enough
GR
distance, you don't have to worry about the
Yeah.
gravitational correction. Okay. General about these.
And the fourth equation, the dE by dt is a vector, then you've got a del dot.
No, that's not a vector.
That's energy.
It's energy.
Oh, that's energy. Oh,
Yeah.
okay. That's my fault. E. I'm thinking E. Okay, got it. Yeah.
Same thing. That's
Yeah, sorry, backfired there. Okay, got it.
Your video, a bunch of the mass just shoots on past the black hole. Is that just it's traveling too fast at that point in time for it to be
Right.
caught back in?
So it's not, yeah, so it's not gravitationally bound. As you can see in the video, a lot of that mass does come back. So maybe in future simulations we will extend our grid spacing so that we can see the total amount that's coming back. But
You show the video again?
yeah,
It's about how much of the mass was captured.
Yeah, that's all I'm going to.
I can't give you a number because we haven't ran any data analysis on it. But once we do, I'll tell you.
The actual physical thing itself is so marginally like just seesaw balance versus bound versus escape. I mean, if you actually just run the numbers on the cloud like a point mass, it's within like 40% bound, not bound.
So it looks like you lose quite a bit, yeah.
How well do we know about this cloud? Because you said you don't know the angle of the orbit it's going to take, so I'm guessing we don't know exactly how this cloud's moving in.
Right. So, yeah.
But it's heading towards the black hole, though.
Mhm.
Do you know other astronomy groups that right now are watching this? I'm assuming they are.
Oh yeah, there's tons. You can just Google it and it's all over like breaking astronomy news.
What are they saying? Is it actually then within a range where they can say it's interacting, or is it still?
As of like right now, currently?
Yeah, you said mid-2000.
Mid 2013. Yeah, so it's supposed to have already come into contact by the observations that I was reading, but it seemed like I would like read observations from like 2011, and then I read observations from 2013. That time would keep changing and getting longer. So if it's actually come into contact with it as of now, I'm not sure. I did have an app on my phone that was kind of like monitoring it, but yeah. So, and I think it'll take a while for those actual observations to come out and get processed, and so that we can actually look at it and compare our results. So I don't know if it's actually come into contact yet, or if it's still in the
Has
process.
it got a name? So when we Google it, what's it called? This?
G2.
Oh, just G2. Okay, I missed that bit.
Yeah.
Look at that. Actually, can you go back to the cartoon? Maybe maybe a slide back. There, that one. So the parameters that you supply are what? All those numbers there?
Yeah. So
The distribution of velocities?
yeah. So
Right, it's not indicated here, but.
the velocity, I don't know if you can see it. Is
Right, no, but is the distribution of velocities of the, okay, so within the cloud. And how do
within the cloud.
You know, oh, I see, to density, but you got a velocities in the cloud, right? On the right? Is the velocity, some sort of velocity field, is that correct?
So you're treating the cloud as being static itself, and then
It's got a temperature, so you got thermal.
It's got a
relative to its
velocity
motion.
distribution for reasons observers like to put in. It's really complicated technically, and I didn't bother him with the details.
right. So it's just
Because
the
it's-
whole cloud's moving in something.
It's got a huge turbulent velocity field inside of the cloud also, but yeah, I didn't,
Gotcha.
beyond the scope of really being important.
So the things that you vary all those numbers in that table, is that correct?
right.
Okay. And did you just run the one simulation, or have you done like three?
We ran a lot of simulations, but the only one that we were happy with was the one that I showed for various reasons. So it was a long process of trying to fit what was going to work, fixing things in the code, stuff like that. Yeah.
Any more questions for our speaker? Hey, go
Sorry.
ahead.
Just what happens
I love
the
this
cloud
question.
that gets like caught in this black hole? Like, can you are you learning anything about black holes? Like, can you draw any conclusions from this stuff that's stuck in that black hole?
Can we draw any conclusions?
Or would it be possible even to do that? Like, what's-
So we're more specifically interested in the interactions between the black hole and the cloud, and basically seeing if this MHD, if these equations are a reasonable explanation of what's going on between these interactions. Any specific conclusions about the black hole itself? Not really.
The input of the black hole comes from G, right? The gravitational potential. That's how it's affecting your code, right?
Yeah.
Yeah.
Actually, I'm not sure if you would know the answer to this, maybe Jared does, but this thing is, swallowing up these charged particles, right? Is it acquiring net charge in some way? Does that ever matter?
The black hole.
Black hole, yeah.
I have
does it
no
char-
real good understanding what a charged black hole even means.
Well, that's what I want to ask.
I'm not that one.
Okay.
There are,
Chad
there are
might-
calculations for a charged black hole, and that's, what is it, the Kerr black hole solution. So,
Isn't it the Nordstrom one? I thought Kerr was the.
Yeah.
maybe it's Kerr, you're right. No, I always mix them.
Yeah,
Nordstrom,
exactly.
yeah, Reiser Nordstrom, that's right.
One thing you can do with this that's interesting, like observationally, is it's more precise to say that they have localized 4.31 million solar masses of material to within a certain range of sort of spatial sizes. If you observe this, you can further localize it down, because what you really want to do is you want to get that mass localized to a region of space where it can't be anything else. If that makes sense. You can say it's in an even smaller region than the region we already say it's in.
So is the simulation going to tell you this?
No, you would have to do, no, I would, that
Direct observation.
one is remap the whole thing to where you're actually resolving GR effects. But
Oh.
the scale of this is too large to say anything about localization.
Yeah, because
Someone
basically,
will do that.
So a grid size in solar system AUs, do you know what the grid size is? I know you made it finer around black, I doesn't matter. Yeah, parsecs, I can't quite, I'm not good at, I don't know, it's fine.
That's what, 3 parsecs for a light year, is that right? I always mix this stuff up.
3.26 parts.
Yeah, somewhere around.
So that's a light day, solar system maybe, I'm just guessing.
I don't know why they have to change the units so much.
Yeah, it kills me.
That's a great question.
Yeah.
How do you observe this occurring? What are the observations based on?
Like of the actual event happening. They're based from astronomy, from,
What do they see?
I can show you. This is what they see. Right? What else do you need?
How do they know what they're saying? Like, how do you know what that's?
What do you mean? What else do you need? There's,
You know what I mean?
you have the cloud, the black hole, it's going there.
So you can observe, the electromagnetic radiation, you can look at the distribution of the wavelengths, right? So
Right.
they do these
Yeah,
different
so for
telescopes to see, so you know all the makeup of the.
Yeah, how do you know
electromagnetic-
type, maybe you can explain how you know type of rings, for instance.
Spectral analysis and all that.
Yeah, right. But I know they're just, they don't really care.
That's a good question.
Making sure you have your faces covered, you know?
They're just pulling my leg.
Coming, yeah. Any other questions for our speaker? All right, Tom.